this video, I want to demonstrate how to estimate vector error correction model. Yeah, I want to assume you set your working directory, so I'm starting from data importation. So let me run the line of code in line 1 to import my data set. Now I've imported my data set. You can see the code is run. You can see the data set here. Now I want to transform some variables. So I need tidyverse or that package, but I prefer to use tidyverse. Okay. Now let me load the package tidyverse. Then I want to transform nominal UDP and log and money supply to log form. So let me transform that. So it has been transformed. So now to estimate vector error correction model. So we follow the same procedure. The same thing we did when we wanted to estimate our VAR model, that's VAR model. So we are going because we are going to use the same package VAS to estimate both vector autoregressive model, that is VAR model, and vector error correction model. So the same package VAS, that's what we are going to use. So let me load the package VAS, then just like VAR model. So the first thing is to select the optimal line using the function. So this function is not a string to you because we have used it for optimal line selection under VAR model. So now we are using this three variables. So these are the three variables we want to select. So now let's check. So here is the function we are using, VAR select function, available in VAR package. So this type means that we want to include constant specification. So now let's run that. So the optimal lag according to this is 2. You can see I'm going to AIC because we are using AIC criteria. Yes, AIC criteria, that's what we are using. So we have lag 2, meaning that the lag 2 is the optimal lag. Okay, so lag 2 is optimal lag. So after that, in order for us to run vector error correction model, so our variables must be I1, that is must be stationary at first difference, and they must be co-integrated. So in order to check for co-integration, among our variables, so we need the library called URC. So this package URC, so we are going to load it. So with this file, we'll be able to run Johansson co-integration test, which is suitable for multiple equations like what we have under VAR and vector error correction model. So let me load the package URC so that we'll be able to run our co-integration test. So let's run code. So the library has been loaded. Then Johansson co-integration test. So the function we are going to use in URC is what we call ca.jo. That is the function we are going to use. So in this function, the argument we are going to put, so we are going to put the variables. You can see here are the variables, the same variables that we use in our VAR select here. So these are the variables involved. So then we have health date. So we can have whether to include, so we are including constant, right? Constants here. Type, we have trace because Johansson test has two series of tests. We have trace test and eigenvalues test. Okay, eigenvalue test. You can see trace and eigen. You can see that. So this K here means the number of lag. So we are able to determine lag 2 as the optimal lag. You can see, and we have spec. So we write long run here, long run. Okay, now let's run that. So now after running that run, so let's see the result. So the result, you can see the result now. So we go up. Here is what we need. So we start from the bottom here. That R is equal to 0, meaning that no co-integration. No co-integration, that's what it means. No co-integration. Okay. So if this is rejected, so we are using the conventional level signal, which is 5%. You can see that 43.80 is greater than 34.91. So we reject the non-hypothesis of no co-integration. Okay, so if we reject the non-hypothesis, it means that there is at least one co-integration. Okay, there's at least one co-integrating equation. That's what it means. Because if we say we reject the non-hypothesis of no co-integration, it means that there is at least one co-integrating equation. So now we move to the second one. So we can see this t-test value, this 18.05 is less than 19.96. So we could not reject the hypothesis that the co-integrating vector is equals to or greater than 1. So it's so, meaning that we cannot reject the hypothesis, so we stop here. So we conclude that there's at least one co-integrating equation according to do this trace test. Okay, now let us also see the eigenvalue. So whether the conclusion will be different. Let's see. So the only thing that has changed here is this to change this trace to eigen here. So let me run this too. If I run this, then let's see the result. So go up. So we can see this the test value is greater than 22.008. Yes, we get the non-hypothesis of no contribution. Then here we move to this one. So we could not reject this non-hypothesis because this 15.53 is less than 15.60. So we stop here too. So we concluded there's at least one contributing equation. So we reach the same conclusion whether we use eigenvalue or trace test, okay, to draw our conclusion. So having established co-integration among these three variables, log of nominal GDP, log of money supply, and anything. So we are good to go. So we can now estimate our vector error correction model. Vector error correction model. So this vector error correction model, so we are going to use, what we are going to use here is that we want to function called cardio LS, that's or cardio RLS. So that we are going to cardio RLS. That's what we are going to use. You can see cardio RLS. That's what we are going to use. So here, so we want to this RLS. Okay, let's list RLS. So we can see. So here is just anything. So we can use this dot RLS to differentiate this variable name from the one we use for co-integration. So this is the most important part, okay? Then cardio LS, yeah, the CAJORLS. So now in bracket we have VECM, that is the variable, the result of our co-integration here. So we put it, so we want to transform that to VECM. We want to transform our co-integration equation to a vector error correction mode. That's what we are trying to do. Okay, so now we put in comma half, that is a number of co-integrating vector. So equals to 1 because we only established one co-integration. So there's one co-integration. Okay, there's one co-integrating equation according to our result of co-integration. So we write 1 here. If there are two co-integrating equations, we write 2 here. So now let's run this. So see, as we've run about, we won't be able to see our result until we use the functional coefficient, or if we like summary, okay? So the summary is larger than coefficient, so let's use coefficient. But we are going to put this and this last, so we have RLM, RLM. So we are going to add RLM there. So we want to extract RLM from our result. So we run the last one here, so you can see our results. Let's go up. Let's go up. Start from the very first one. You can see here for the first equation, so log of nominal GDP, you can see these are vector error correction model. You can see the coefficient of the error correction term, okay? So you can see the coefficient of the error correction term. So this implies there is a long-run causality, okay? Relationship, okay? Because this is confirming there's long-run relationship among these three variables. There's long-run relation among these variables, okay? Now, moving to the second one, moving to the second one, you can also see that it's significant, okay? It's also the significance, okay? So this one is saying that if the dependent variable, this first one is if the dependent is log of no, nominal GDP, if the dependent is log of nominal GDP, so it implies that this money supply and lending rate, okay, money supply, lending rate, and money supply and lending rate are actually Granger cost, jointly Granger cost, log of nominal GDP. That's what this implies. Okay, so we can invert Granger causality from here. So here, this one, since this one is also significant, negative and significant, okay, is negative are also significant. You can see negative as significant. If you look at that law, we can see negative as significant. So it also implies that lending rate uh, and the other. So let's see this one is from lending Jones Granger calls log of money supply. That is what we mean. So moving to the last one. The last one, this is not significant. Okay. So it implies you look at the equation, this equation is for lending rate. So this implies that log of nominal GDP and log of money supply does not do not jointly Granger cause lending rate in the long run. Okay. All these Granger calls we are talking about long run. So because EC, as a question term represents is a long run phenomenon. Okay, that is it tells whether the dependent variable, the independent variable actually Granger cause sees the dependent variable in the long run. Okay, so we interpret in long run. That's we interpret in long run. So that is that. Thank you.